All right, so I'm gonna work more problems from 4.9, which is again antiderivatives. Remember, antiderivatives or integration, right? That's what this means right here. That's another way of saying it. Is going in the reverse direction of deriving, right? So remember, if we have little f of x, that's the original function. If we had little f prime of x, that means first derivative, right? Of the original function. And then if you saw like big f of x or big g of x or big whatever letter of x, that means the antiderivative of your original function, f of x in this case. So if I were to go, up in this direction right here, that would be us deriving, right? But if I was going down, right? Like if I was going down this way, we would be integrating. So remember, integrating means finding the antiderivative. And we did it for some basic types of functions, right? Really, we only did it for algebraic functions, right? Like if we had to find this, right? Remember, this means the integral or the antiderivative of x to some power of n with respect to x. And we talked about you had two types of integrals, right? You had an indefinite, which had no limits, which this one is right here, or you could have a definite integral where you would have terms placed inside right here. But for now, we're only dealing with indefinite integrals. So how did this work out? Remember, it's the reverse of taking the derivative. So remember, for the derivative power rule, you would say n times x to the n minus 1. But since we're anti-deriving, we're going to do the reverse of that. So that's going to be x to the n plus 1 over n plus 1. And then don't forget our constant, right, plus c. Because remember, since this is an indefinite integral, or we're basically finding the general antiderivative, there's numerous solutions to this right here. Remember, how can we check our work for the antiderivative? If we were to sit there and take the derivative of the antiderivative, we should be able to get back to our initial answer. So right here, if I were to derive any constant, you get 0, right? If I were to derive this, I would get back to here. Now recall, if we had an example, like let's just say we're going to integrate x to the fourth dx, right? Well, if we did the I'll call it the power rule for antiderivatives, this would be x to the fifth over 5 plus c. Now remember, c is a constant, right? It could be plus 10, minus 8, plus pi, whatever, minus square root of 15. It doesn't matter, because if you were to derive this, right, if we derive this, if you derive x to the fifth over 5 plus c, you get 5x to the fourth over 5, right? And remember, c is a constant. Derivative of any constant, 0. And this is just equal to x to the fourth when we reduce it. So you see, we get back to our answer, or I'm sorry, our initial integral. That trick of you checking only works when you don't have limits to integrate with, right? So let's talk about what are some other things that we can integrate, because I only mentioned algebraic expressions. What about trig? Do trig functions have antiderivatives? Yeah, definitely. Exponential functions have uh, antiderivatives as well. So I'm just going to make a little list of common ones that you'll see. I'll make a table. So if you have, we'll start with e to the x. So if the original function is e to the x, the antiderivative is also e to the x. I kind of talked about this when we did the derivative of e to the x. And I said, oh, it's a unique case. The function e to the x is the only function in all of math whose derivative and antiderivative are itself. So it's just e to the x. What about, say, cosine of x? What's the antiderivative of that going to be? Sine of x. Or the derivative of sine of x, I'm sorry, the antiderivative of sine of x is going to be negative cosine of x. Now, how do you check these right here? Well, remember, if I take the derivative of this, I should get back to here, right? So if I take the derivative of an antiderivative, I should be able to get back to my original function. So what's the derivative of sine of x? Cosine of x. What's the derivative of negative cosine of x? It's a negative sine of x, which gets you back to a positive sine of x. Be very careful with this one right here, all right? Because a lot of people confuse these two. Why? What do? They say, oh, if my function's cosine of x, the antiderivative is negative sine of x. No, the derivative of cosine of x is negative sine of x. The antiderivative of cosine of x is positive sine of x. Again, to check it though, derive your answer. What's the derivative of sine of x? Cosine of x, right? What's the derivative of negative cosine of x? So if you block out the negative at first, the derivative of cosine is negative sine. But because you have a negative in front, a negative gets you back to a positive. Remember, I'm taking the derivative of the antiderivative when I'm talking about that, or what I just spoke of. What if you have secant squared of x? If that's your original function, the antiderivative is tangent of x. For the trig functions, what's kind of nice is you can ask yourself, what can I take the derivative of that's going to bounce me back to here? So if you have secant squared x and you're trying to find the antiderivative, you can think, what's a function that I can take the derivative of that's going to get me back to here? Oh, it's tangent. Because what's the derivative of tangent? Secant squared, just like that. Or like if I have secant x tan x, you can think, all right, what function, if I take its derivative, is going to get me to secant x tan x? It's secant x. That's the antiderivative. So again, if I take the derivative of secant x, I get back to secant x tan x. So we know that this is the antiderivative of this right here. Or if I have this right here. Remember, we saw this when we did implicit differentiation a few sections ago. That's just the arc sine of x. That's the antiderivative of that. Remember, if you took the derivative of arc sine of x, you get back to here. Or if I had 1 over 1 plus x, well, let me erase this. If I had 1 over 1 plus x squared, if I approach it the same way that I did this one right here, what function could I take the derivative of that would bounce me back to here? Well, whenever you have these 1 over 1 plus or minus x squared under some roots or not under root like this, it's probably some kind of arc function, and it's the arc tangent of x in this case. Another one that's important is this one right here, 1 over x. The antiderivative of 1 over x is the natural log of the absolute value of x. It's really important to have the absolute value. And think about it for a second, right? Is this true? What's the derivative of natural log of stuff? It's 1 over stuff times the derivative of the stuff. So if we took the derivative of natural log of x, it's 1 over x times the derivative of x, which is 1. So you get back to here. But again, the absolute value is very important right here. So these are some common ones that you should remember because they pop up a lot, okay? Now, what if we have, let's see here. Let's try some where we mix all this stuff up. Like, let's say we have f of x is equal to, I'll say 2 cosine x plus secant squared of x, like that. And we want big f of x. Remember, when you go to the big letter, they want the antiderivative. So what we're trying to do is this, right? We're trying to integrate 2 cosine of x plus secant squared of x dx. So what is we can just basically go across, right? We know the derivative of this and the antiderivative of cosine and the antiderivative of secant. When you're taking the antiderivative of something, if you have stuff separated by an addition or subtraction sign, it's okay to split it. Meaning if I have the integral of a plus or minus b dx, for example, where a and b are like any kind of algebraic function, trig function, whatever, you can split that integral, but say, oh, that's the integral of a dx plus or minus the integral of b dx, like that, and work out each part piece by piece. So if we look at this, we can go out there and integrate it, right? If it was multiplication, though, it doesn't work out the same way. We can't sit there. You cannot do this. Like if we have the integral of ab dx, that does not equal the integral of a dx and then times the integral of b dx. That is not true. Same thing with division. Like if we have the integral of a over b dx, we can't sit there and say, oh, that's the integral of a dx over the integral of b dx. We can't integrate it like that. So multiplication and division make things a lot more complicated. But if it's addition and subtraction, then yeah, we just go ahead and split it up. So coming back to this, right? I'll just work it right here. What's the derivative of cosine of x? Well, we just saw that, right? And again, you can think, what's a function that I could take the derivative of that would bounce me back to cosine of x? It's sine of x, right? So it's 2 sine of x. Now with this constant, whatever you have in the front, you just drop it down. And then what's the antiderivative of secant squared? Well, again, you want to think, what's a function I can take its derivative of that bounces me back to secant squared? It's tangent, right? Tangent of x. Because what's the derivative of tangent? Secant squared. What's the derivative of sine? Cosine. And then don't forget your c, right? And on WebAssign, make sure it's an uppercase C. Why do we need a C? Because this is a general solution or a general antiderivative to this function right here. Remember, if I were to check this, what would I do? I would derive this right here, and I would bounce back to this original function. This plus C means any constant, right? And the derivative of any constant is always 0. So that's why we have this plus C right here. The C can disappear. It will if you have limits right here, which we will do in a section coming up. What if I have, I'll do this now. Let's say we have f prime of x equals secant x tan x minus 8 e to the x, and we want f of x. So right here, we were given the derivative, and they want the original function. So what does that mean? We just have to go out there and take the antiderivative, right? It's the same thing that we did right here. It's just that Right here, what do we start with? We started with the original f, and we wanted the general antiderivative. Right here, we're starting with the derivative, and we're just trying to move to the original function, or back to the original function. It still works out the same way. So f of x is the integral of f prime of x with respect to x in this case. So that's the integral of secant x tan x minus 8e to the x dx. So we have this minus sign here. We can just split it, right? We can integrate each piece right here. That's okay. So when you do that, remember, you want to think, what can I take the derivative of that's going to get me back to secant x tan x? Because whatever that function is, it's got to be the antiderivative. So that would be secant x. Why? What's the derivative of secant x? Secant x tan x. But the antiderivative, remember, if you go in the reverse direction of secant x tan x, that would be secant x. Now moving along to this piece right here, what's the antiderivative of e to the x? Remember, the antiderivative of e to the x is just e to the x. And because we have that constant right in front of it, we just bring it on down. So it's minus 8e to the x. And then don't forget your plus c. Remember, you can check this, right? How do we check if the antiderivative was correct? Because if I derive the antiderivative, I should get back to the original problem. What's the derivative of secant x? It is secant x tan x. What's the derivative of minus 8e to the x? It's minus 8e to the x. What's the derivative of any constant? Plus c. What if I have f prime of, I'll say t this time, it doesn't matter. F prime of t equals 3t to the fourth minus t cubed plus 6t squared over t to the fourth. And again, we want f of x. So we started with the derivative. We want to go to the original function. How do we do that? We take the antiderivative. So f of x again is still equal to the integral of f prime of, well, I'll say t this time because we have t right here. F prime of t dt. No longer x because it's all in terms of t this time. So we're trying to integrate this whole thing right here with respect to t. So if the letter changes, it doesn't matter. The rules still work the same way, okay? It's dt and these are t's. You would do it as if it was x and a bunch of n dx as well. Now, how are we going to do that, though? Because, like I said, with division, you can't say, oh, it's the antiderivative of the top over antiderivative of the bottom. So sometimes you'll have to manipulate these right here. Well, what can we do? Well, we could somehow, break it apart into smaller chunks, like break it apart into just the addition and subtraction of this expression without the division part, right, like this. Then we could go out there and integrate it. And we can, because we can take this t to the fourth and divide it into every single piece, right? Into here, and then the t to the fourth into this chunk, and then also into this chunk, right? So remember, when you divide the bottom, it has to go into everything up top. So that's what we're going to do individually right here. So if I divide 3t to the fourth by t to the fourth, the red, what's left over? You're just left with 3 because the t to the fourths cancel. Don't sit there and make the mistake and go, oh, I'm going to cross out this t to the fourth, t to the fourth, done, and then write the rest of the problem. No, you need to divide this t to the fourth into everything up top. Now we need to divide the t to the fourth into the negative t cubed, right? What's t cubed over t to the fourth give us? That would be minus t to the negative 1 power, because you do top exponent minus bottom. What about the blue? What's 6t squared divided by t to the fourth? That is 6t to the negative 2 power, because 2 upper exponent minus bottom exponent, 2 minus 4 is negative 2, And then we have dt right here. So you notice now, oh, we were able to just manipulate it, right? Get rid of it, get rid of the division so that it wasn't just something divided by something like what we had right here. And now we can integrate or find the antiderivative of these individual pieces. So the integral of 3, or the antiderivative of 3, is, it's just 3t, right? Remember, how can we check this? If I take the derivative of 3t with respect to t, what do you get? What's the derivative of 3t? 3. So we know that's correct. What about this one right here? So remember, t to the negative 1, that's 1 over t. If we had to integrate 1 over t, that's a special case right there. Anytime you have 1 over some variable to the first power, it's that natural log. So it's natural log of the absolute value of t. Don't forget that right there. So this is minus ln absolute value of t in that instance. You may be asking, well, why can't we do the power rule on that, right? The power rule, like what we've been doing. Because what happens if we did? Like, let's say we did that, right? Like you have t to the negative 1, and you just try to integrate it using the power rule for antiderivatives. What does that say? That says, oh, you'd say t to the negative 1 plus 1 over negative 1 plus 1, right? If we were treating it like a purely regular old algebraic expression. But what happens right here? You get t to the 0 over 0. But what's anything divided by 0? That is undefined. That's why we can't do the power rule on it. This is just a special case right here. So remember, anytime you have a variable or 1 over a variable to the first power, or even a constant over a variable, this could be 5 or 10, it doesn't matter, okay? But once you have a number over a variable to the first, it's that number, natural log of the absolute value of that variable all the time. Very important. Now, what about the next piece? Well, right here, if we do the power rule, what happens for antiderivatives? We get 6t. Remember, it's negative 2 plus 1, which is negative 1, over negative 2 plus 1, which is negative 1. Don't forget your plus c, right? So we have that. So now let's go out there and clean it up. How can we clean it up? Well, this is still 3t minus ln of the absolute value of t, and then minus 6 over t to the first plus c. So this negative comes from positive over negative. That's a negative. What did I do right here? The t to the negative 1, I made it positive, and to do that, you have to flip the exponent, right? So that's 6t to the first. Remember, only the t will drop down. Why? Because only the t has the negative exponent being applied to it. The 6 does not have a negative exponent, so it still stays up top. And of course, if don't forget your plus c, and make sure it's uppercase on web sign, because as I've mentioned before, if you put lowercase c, it's going to mark it wrong for some reason. Now, of course, you could always check this, right? If we took the derivative of all this stuff right here, we would get back to our original integral. All right, let's see now. Now, what if we have f of x equals 2 and then 7th root of x plus 6 sine of x, and then we want big F of x. So we're going from the original function, right, to the uppercase of it. Remember, that means antiderivative. I changed it up again. But remember, to find that, big F of x is equal to the integral of f of x dx. So in the last two problems, what do? We took the antiderivative of the derivative to get back to the original function right here. Again, it's just different notation, but we're doing the same thing. So how do we do that right here? this would be 2. And remember, whenever you have radicals and you're deriving or anti-deriving, you want to write them out in exponential form. This is x to the what power? The 1/7, right? Whatever that index is, that's your denominator of your fractional exponent, plus 6 sine of x dx. Now, what do we do with this right here? We can go ahead and take the antiderivative of each of these respectively because they are separated by addition or subtraction. In this case, it's addition. So we do the power rule on this one, right? Because it's an algebraic expression. How do we do that? Well, this is 2, and then x to the 1/7 plus 1 over 1/7 plus 1, right? Because it's x to the n plus 1 over n plus 1 when you're finding the antiderivative. What is the antiderivative of 6 sine of x? Well, I'm going to drop the 6 down for now. But what's the antiderivative of sine of x? Remember, it's negative cosine of x. Be careful because the derivative of sine of x is cosine of x, but the antiderivative of sine of x is negative cosine of x. Remember, how do you check this out right here? If y is equal to negative cosine of x, what's y prime going to be? That's going to be negative sine of x, which is positive sine of x. What did I just do right here? Well, as I've been saying, if you take the derivative of your antiderivative, you should get back to your original function. So if I take the derivative of negative cosine of x, I should get back to sine of x, right? Which I did. I just showed it right here. And don't forget your plus c. So obviously we need to simplify, right? Especially this part right here. So what is this? This is 2 and then x, and what's 1/7 plus 1? That's 8 over 7. That means we also have that divided by 8/7. And then this is just minus 6 cosine of x plus c. Then of course we can simplify this, right? So remember, when you have that fraction or a number over a fraction, you can rewrite this, right? This is the same thing as saying 2 times 7/8. You just flip this and bring it up top. So 2 times 7/8, x to the 8/7 minus 6 cosine of x plus c. And then we can simplify further, right? Like this reduces right here. 2 crosses out with the 8. It reduces that to a 4. So we get 7/4 x to the 8/7 minus 6 cosine of x plus c. So there would be your final answer right there. Again, it's just because we're able to reduce this right here, right? That's where that 7/4 comes from. So what's the significance of antiderivatives? So with derivatives, they gave us the instantaneous rate of change, right? We could figure out how fast we're moving at some instant, right? So how does that apply to more, I guess, real world usage, right? Well, definitely in physics, right? So you'll see this a lot for those of you who are doing engineering. You'll usually have something like S of t. We call that like a position equation. And then you'll have v of t. That's a velocity equation. And then you also have a of t. That means acceleration, right? Acceleration. So if you take the derivative of a position equation, you get to velocity. Take the derivative of velocity, you get down to acceleration. So this is deriving if we go down. And then if we go in the reverse direction, right, like this, then that's taking the antiderivative. Derivative. Antiderivative. So how can we use this right here? Well, sometimes you know the acceleration of an object and you're trying to get its position equation. How can you do that? By let's say we have a particle is moving with the given data. And we want to find the position of the particle, or the position equation. So we have v of, let's start with this one right here. We have v of t equals sine of t minus cosine of t. And they give us this right here, this piece of data. Find what's the position equation going to be? Because remember, these equations are changing at every single instant. What's the position going to be at basically position 0, or like t equals 0 seconds, if you want to look at it like that? Well, we have the velocity equation. To get to that position equation, right, we need to go ahead and take the antiderivative of it. But this piece does play an important part into it later on. So s of t is equal to the integral or antiderivative of v of t. And in this case, it's the antiderivative of sine of t minus cosine of t dt. So what's the antiderivative of sine of t? It's, remember, negative cosine of t. If I take the derivative of negative cosine, I get to positive sine. What's the derivative of cosine of t? It's sine t, right? But it's going to be minus because of this minus right here. And then plus c. So the way these particle physics problems differ from the ones that we've been doing is that we're going to figure out what this c is right here. We can do that, okay? How? It's from this data that they gave us right here. Remember, this is just, we have basically found s of t right here. What we need is we need c. How can we do that? We can substitute these values in, right? Remember, this is like this is function notation. This is like saying this is x, right? When x is equal to 0, y is equal to 0. That's what it's saying in this case. So what are you going to do? Substitute those values in for here and solve for c. So what happens? We have, well, s of 0, they said, is equal to 0. So remember, this is the y right here. So that's 0 equals negative cosine of, and then we're going to dump this 0 in, okay, into this side of the equation. And now let's solve for c. Well, how are we going to do that? Well, evaluate, right? What's cosine of 0? 1. Well, there's a negative out front, so it's negative 1. What's sine of 0? That's just 0. And then we have plus c. So what does c have to equal when you solve it? You get 1, right? Because I just add 1 to the other side. So ultimately, what is your final answer right here? It's going to be s of t equals negative cosine of t minus sine of t plus 1. That would be your position equation at that specific instant that it was asking you for. Notice I just basically took the antiderivative, the general one that we got, and whatever c was when we solved it, you jammed that number value into there, just like that. Now, what if we had this instead? Let's say, what if we were given the acceleration equation and we said, oh, a of t is equal to 2t plus 1, and they said s of 0 is 3, and then v of 0 is negative 2. So this time they gave us 2 data points. Why? Because we're starting with acceleration. Remember, if you take the antiderivative of acceleration, you only go up to velocity. Then you have to take the antiderivative of velocity to get back to the position. So basically, we have to take the antiderivative 2 times right here. Kind of like if they said, find the second derivative, right? You derive your original function twice. Right here, we have to integrate twice. So we need v of t first. V of t is equal to the antiderivative of a of t. And in this case, that's 2t plus 1 dt. So what is the antiderivative of 2t? Well, remember, that's just 2t squared over 2, which we'll reduce in a second, plus, what's the antiderivative of 1? It's just 1t. And then we have plus c. So this is v of t right here. So we know that that's t squared plus t plus c. But now we need to solve for this c right here. How are we going to do that? Remember, this is our x and this is our y right here. So now we're going to say, oh, -2 equals, and we're going to plug zeros in for all these t's right here. 0 squared plus 0 plus c. So we could see instantly that c is equal to -2. So now we have our general velocity equation. Your general velocity equation is t squared plus t plus so your general equation is t squared plus t, and then c is -2, so we're going to have -2. Now we're not done, right? Because it was asking us about the position. So now we need s of t, right? So I'm coming down here now. S of t, the position equation, is equal to the antiderivative of your velocity equation. So in this case, it's going to be, what's the antiderivative of the integral of t squared plus t minus 2 dt. All right. So what is the antiderivative of all that stuff right here? Well, the antiderivative of t squared is 1/3 t cubed plus, what's the antiderivative of 2 to the first? That's 1/2 t squared, or t squared over 2, it's the same thing. And then what's the antiderivative of -2? It's -2t. And then we also need our plus c. So this is what s of t is equal to. Now we need to figure out, what is this c component going to be? Well, how are we going to do that? Well, we're going to use this one, right? This is going to be the x, and this is going to be the y this time. So now we're going to say 3 equals, and I'm going to throw 0 in for all these t's right here on the right side. So we're going to have 1/3, and then 0 cubed plus 1/2, 0 squared, and then -2 times 0 plus c. So what does c equal in the end? Well, these aren't too bad, right? Because this is all zeros right here. Will it always be 0 something, 0 something? No, it could be 5√8 if they want to make it up like that. They'll specify it. But when we solve this, what happens? That's 0, 0, 0, c. So we get 3 equals c. So what is your final answer to this particular problem? Because remember, they were asking for what's the position equation. So in this case, we have it. It's 1/3 t cubed plus 1/2 t squared minus 2t, and then plus 3. That would be your final answer if you were asked for the position equation at this specific point right here. So you're going to see this a lot in physics, okay? And then for those of you who go into engineering, all your systems that you're going to be working out, you're going to do something like this right here, where you're going to start with, it's not going to be acceleration, it'll be some other thermodynamic concept or whatever, and you have to integrate and work backwards and backwards, pretty much like that. And you're going to be solving for constants and constantly rearranging and manipulating your equation as it goes on. So again, this was still the 4.9 stuff, right? It's very important that you know these basics like this, like the power rule stuff for antiderivatives. And from that list of generic antiderivatives, like the antiderivative of 1 over x is natural log of x. Those trig functions that I wrote down, you need to know the antiderivatives of those because they will come up a lot. Okay, that is it.